Hi. So, now that we've done all the hard work, it is time to solve the model. However, before we go there, I just want to point out one important thing. Look, we were assuming that parameter J, so when we had a change in expected inflation, was given by the difference between actual and expected inflation. And look, in this, in the context of this model, J is crucial. Okay, we were assuming that J is bigger than 0. However, we should make some additional restrictions on J here, and I wanted to explain to you why in terms of economic theory. Look, this equation is telling us how expectations about future inflations unfold. Now, the thing is, we are assuming adaptive expectation. So, households, so generally workers, customers, make their expectations about the inflation, taking into consideration their mistakes in the past. And look, here we've got parameter J that definitely needs to be positive. However, it is crucial to understand what is going to happen if J is between 0 and 1, or 1 at most, or when it's bigger than 0. Look, if J is between 0 and 1, right, it means that if, for example, let's just say that J is 1.2, right? I'm sorry, 1 over 2. Now, if actual inflation is, let's just say, 3%, and expected inflation is 2%, we've got 1% inside, right? And it means that the expectation about future inflation is going to be 1 percentage point higher, right? Now, what if J was 8? If J is 8, then 1 percentage point difference between the two would translate to 8 percentage points increase in expected inflation, with all the consequences of that, right? And as we know, even from our function, from our Phillips relation, actual inflation depends on expected inflation. So, if parameter J would be above 1, we could expect that that we could find a source of explosion in the model. What I mean by explosion is that getting out of the equilibrium. And look, it makes perfect sense, because if J is bigger than 1, it will translate to, let's just say, very, very unrealistic and very unrealistic expectations about future inflation and extreme growth in the expected inflation. And through that, it's going to spread through the model. So look, I'm going to do one very specific, I'm going to take one very specific assumption for our model to hold. I will explicitly assume that J is always between 0 and 1 close. This is enough for us to actually ascertain stability. Okay, the second thing that I wanted to do, just to make all the calculations easier, in comparison with previous, what I want to do is that this is the time that, this is the difference equation that we found, right? To make things easier, I want to take minus out of this parenthesis. So here we're going to have minus, and here we're going to have 1 minus g, right? Still, everything stays the same. However, it will make our calculations easier when we move later on. Okay, so first thing, of course, now we need to find the time. So we should start with equilibrium solution. So equilibrium level of inflation. So particular solution. So our equilibrium level of inflation is given by C over 1 plus A1 plus A2. Okay, our C is J, K, beta, M over 1 plus beta, K. We divide this by 1 plus, and our plus is actually here minus. So we've got minus 1 plus JG plus 1 minus J times 1 plus beta K over 1 plus beta K plus 1 minus J times 1 minus G over 1 plus beta K. Okay, now look, of course, in order to add those expressions, we need to put them all into common denominator. So 1 is going to be turned into 1 plus beta K over 1 plus beta K. And now look, all those have the same denominator, right? So we could put them all together, and we see that our C also has the same denominator. So when we will be dividing them, the two will cancel each other out, and what we are going to have over here is going to be J, K, beta, M over whatever we get out of all of this. And what will we get? Okay, 1 plus beta K, now minus 1 minus J, G, plus 1 minus J times 1 plus beta K. And look, let's get rid of couple of things right away. We can get rid of this expression, and here we've got 1. Of course, here must be minus. We put minus in front of everything. Look, here out of this we will have negative 1 times this. So those two. Again, so those two must be cancelling each other out, and out of this entire expression, what we're going to get is minus minus. So plus J times plus J beta K. Okay, and finally, at the end, we've got plus 1 minus J and plus GJ. Okay, so now we will get even more things that will cancel each other out. We see that those two J's cancel each other out. GJ is cancelling each other out. Ones are cancelling each other out. And our very complex fraction is turned into very simple J, K, beta M over J, K, beta. Those two also cancel each is m. So the first thing that we found is similarly to the model with differential equation, equilibrium level of inflation is equal to the money growth. Okay, and this is our particular solution. So we know what is that model equilibrium. Okay, so now that we found model equilibrium, we can move on to ask the question whether this equilibrium is stable or not. Of course, this means that we need to consider a complementary function. And as usual, with complementary function, there are different possible cases that we need to consider. Okay, look, our a1 squared is equal to, we need to take a1 and take it to the power of 2, so we definitely gonna get rid out of the minus. So we got 1 plus g plus 1 minus j times 1 plus beta k over 1 plus beta k, both squared. Right? Then for a2 is equal simply to 4 times 1 minus j, 1 minus g over 1 plus beta k. Okay, so now, of course, whether we're going to have a case of real distinct roots, real repeated roots, or complex roots, depends on the relative values of these two. Okay, let's compare the two and see, maybe just by comparison, we can see right away that only one case is acceptable. Okay, so look, first thing I'm going to do is to multiply both sides of this inequality by 1 plus beta k squared. 1 plus beta k squared is definitely a positive number, so it will not change the inequality signs. However, this makes our equation look like this. Okay, and look, just by seeing this inequality, we can clearly see that a priori there is not much we could say. Of course, so if I cannot tell you that, for example, this is definitely negative, which it's not going to be, right? This expression, of course, we're going to go back to the assumption with J, but within the assumptions that you see over here, this could be 0 at most, right? So definitely, if this could be 0 to the least, and then we can have a first case, but this doesn't need to be the case. This is why, actually, we need to consider all three cases. Okay, so let's start with the first possibility that usually actually uses the most issues. And so we're talking of course about case number 1. So we will have real, distinct roots. So what would happen if a1 squared would be bigger than 4a2? Okay, and look, let's use B2 is equal to negative A1, right? So we need to take well, A1, so we no longer have it on the blackboard, but you remember that it looks the same as this one without squares, and it has minus up front, so we will get rid of this minus. Turns out that this is simply 1 plus jg plus 1 minus j times 1 plus beta k over 1 plus beta k. Okay, this, as you see, we can easily divide this fraction into two parts. So we will have 1 plus jg over 1 plus beta k, and out of this, right, we're going to just get 1 minus j. Okay, so the question is, what is the value of this expression? Look, we see here that this is definitely going to be positive. Now, this expression, under our assumptions, so that j is somewhere between 0 and 1, tells us that this expression over here can be 0, right? Or if j would be 1. However, we would still have this expression, which means that this would definitely be positive. However, look, again, we see that j is the key to understanding the dynamic properties of the equilibrium. Because if j would be bigger than 1, we could start having issues here, right? Now, the second thing we try is the product of the two, which is equal to A2. And your situation is easier. This is simply 1 minus j times 1 minus g over 1 plus beta k. And look, again, we are arriving at a very similar situation. Under these assumptions, this is always between 0 and 1. Right, I hope you can see that this is a number between 0 and 1, this is a number between 0 and 1, this is a number between 0 and 1. However, we divide it by a number that is clearly bigger than 1, so we need to get something that is between 0 and 1. However, what if j would be above 1? We would have a problematic situation over here. We could get that this expression is actually negative. And this would tell us that one of the roots is positive, while the other is negative. However, look, because both the sum and the product of the two is positive, we can clearly establish that both B1 and B2 are bigger than 0. Okay, but we definitely, so what we've established for now is that they are bigger than 0. But let's go one step further, right? We always also try to trade with 1 minus B1 times 1 minus B2. We already established that this is equal to 1 minus B1 plus B2 and plus B1 times B2. Okay, let's substitute. Okay, so we will have that this is 1 minus 1 plus jg plus 1 minus j1 plus beta k over 1 plus beta Okay, and unfortunately I'll have to continue over here. So we okay, and finally we've got this plus plus 1 minus j times 1 minus g over 1 plus beta k. Okay, so now what should we do? Of course, is to put this whole thing into the common denominator, and we will see what are we going to get. Okay, so 1 turns into 1 plus bk over 1 plus bk, right? Then we've got minus 1 minus jg minus 1 minus j times 1 plus b, okay? And plus 1 minus, I'm already gonna multiply this thing out, so we've got minus j minus jg, and this is all below 1 plus beta k. Okay, let's see what we can get rid of right away. Right away, we can get rid of those two. And definitely we can get rid of course here should be a plus, minus and minus equals plus. So we can also get rid out of these two. Okay, for the rest, we actually need to multiply it further. Probably we could do it at once, but let's do it very slowly and thoroughly, because this will be the key to our solution. Okay, so what do we see over here? And now, we multiply negative 1 by this, so we will have negative 1 minus beta k, and minus times minus gives us plus j 1 plus beta k, which gives us plus j plus j beta k. Okay, and 1 plus beta. Now, what can we get rid of now? Well, those two really cancel each other out. And here, I'm sorry, I forgot, at the end, we've got minus g. And those two cancel each other out as well. So look, what did we get over here? We got j beta k over 1 plus beta k. Look, right away, we see that this is positive, right? All the components here are positive. Look, actually, within the assumption we are working with, we can tell even more. Look, j at most can be 1, right? At most, this could look like that. So we clearly see that as long as j is lower or equal to 1, this expression must be between 0 and 1. Of course, for us, the important thing here is that it is positive. However, this result is definitely truthful and actually showing us that as long as j is lower or equal to 1, the stability of the model is quite remarkable. Okay, now let's consider the cases we don't want. Like, look, if we would have a situation that B1 is equal to exactly 1 and B2 is equal to exactly 1, we would have that our expression 1 minus B1 times 1 minus B2 would be equal to 0. However, is impossible. Now, let's consider another possibility. What if one of the roots would be bigger than 0, and the other root, one of the roots, we already know that they are both bigger than 0, is smaller than 1, and the other is bigger than 1. Okay, then this expression, what could we say about it? Look, if one of those is bigger than 0, this expression becomes negative. This one stays positive, so this is negative. However, we show that within our model, this is impossible. Okay, then let's consider yet another possibility. Can they both be bigger than 1? Okay, if they would be both bigger than 1, if they would be both bigger than 1, then this expression would be bigger than 0. However, we already see that this is impossible. So, consequently, we see that each of these cases is impossible. This also tells us that under the case of real distinct roots, we can be 100% sure that B1 is between 0 and 1, and B2 is between 0 and 1. So consequently, we can say that we've got convergence and, of course, dynamic stability. Okay, so now that we know that under case number 1, we've got convergence, actually demonstrating that the same is going to be true for other cases is relatively trivial. Because at case number 2, when we've got real, repeated roots, so we know that A1 squared is exactly equal to 4A2. The situation becomes very trivial. Look, our B in this case is negative A1 over 2. Right? In our case, we already had negative A1. All we need to do is to just multiply the denominator by 2. We get that this is 1 plus, divided by 2, not multiplied by 2. G plus I minus J, 1 plus beta K. This is over 2 plus 2 beta K's. And look, all the components here are positive, of course under the assumption that J is between 0 and 1, so we can be sure that this expression is positive. Now, the question is this, now we know that the roots are positive, however the interesting part is also whether the roots are between 0 and 1. We can easily check it by taking the square of B, right? This will give us A1 squared to the power of 4. However, as this is the case of repeated real roots, we get that A1 squared is equal to 4A2. So I can substitute, which is equal to A2. And because A2 is equal to 1 minus J times 1 minus G over 1 plus beta K, we know definitely that this is going to be between 0 and 1. And based on these two, we know that B is between 0 and 1. So again, we have convergence and dynamic stability of equilibrium. Okay, so finally, we need to deal with the simplest possible case. Well, under these circumstances. So those are complex roots. Well, okay. So the complex roots case is of course when A1 squared is lower than 4A2. However, the situation here is extremely trivial. Why? Because I hope you remember that convergence under complex roots, depends solely on the value of R. R is equal to square root of A2, which is square root of 1 minus J, 1 minus G, over 1 plus beta K. And look, if this is between 0 and 1, the square root of it necessarily needs to be between 0 and 1, which means that again we have convergence and or dynamic stability. Okay, so what have we shown? Look, we have shown that even though we moved from differential equations to difference equations, we've established that equilibrium level of inflation is equal to exogenously given rate of money growth, nominal money growth. We also show that under the assumptions we have undertaken, this is giving us a dynamic stability, which means if something happens coming strong out of the equilibrium, we move along the short-run Phillips curve, we are going back to that initial level. However, what I want to stress here is that for all our purposes, the most crucial turned out to be the parameter J. Parameter J that is simply telling us about how expectations are adjusted to the differences between expected and actual inflation. So look, this shows us that if households, workers, customers would expect that in the following period, inflation is going to be rising by more than the customers were mistaken in the past. So, if households predict that inflation is going to be getting bigger and bigger and bigger because they assume that the mistake they made could be even bigger in the future. So the disparity will go bigger in the future. The model breaks down in a sense that we will no longer have dynamic stability. And I hope that this shows you how, especially from the perspective of macroeconomics, are important the underlying assumptions about how economic agents form their expectations. Okay, so this is it about inflation and unemployment. Next week, we're gonna see how we can model GDP using a second-order difference equation. Thank you for your attention. Take care.